Okay. Can you see now?
Yes, everything is fine.
Okay, thank you. So I was thanking you, Eti, for the invitation, for this nice opportunity to talk in this colloquium series. The subject today is information disturbance and incompatibility. This will be in quantum mechanics and beyond, as the series title suggests. And this will be about some work that I've been doing in the last couple of years, in collaboration with Mauro Dariano and Alessandro Tosini. And in the last part of something also in collaboration with Marco Erba, who is a postdoc in our group. So before going to the core of the subject, I would like to give you an outline of the things I'm going to say in this talk. And I will start introducing the problem of information disturbance and compatibility in physics, which appeared with Heisenberg's thought experiment. And I will try to make it a bit more modern by recalling the notions within the framework of quantum information theory. And then the idea is to widen the playground where to define these notions and see their interplay. And the playground that I will draw is that of operational probabilistic theories, which is a family of theories which encompasses, of course, quantum theory and classical theory, but has many other, potentially infinitely many other theories with weird and unexplored properties that might turn out to be very interesting for the foundations of physics. And I will introduce in this context the notion of disturbance and see the role that correlations play in this definition, and then define information extraction and see what are the connections between these new notions. In particular, we will see what are theories with information without disturbance or with no information without disturbance. For example, on one side, we have quantum theory, where you cannot have any information without disturbing the system, which is one of the consequences of the Heisenberg uncertainty principle. And on the other extreme, we have classical theory, where on the other hand, you can in principle measure anything without disturbing the system. So you can introduce an arbitrarily small amount of disturbance. So strictly connected to the information disturbance trade-off, there is the notion of compatibility of measurements. So typically position and momentum in quantum theory are incompatible. You cannot measure them simultaneously, jointly on the same system. And we will try to introduce the notion of compatibility in this wider context and see what is the relation of compatibility with the other notions that I introduced earlier. And in particular, we'll define theories with full compatibility and see what are the conditions, what are some conditions that allow full compatibility in your theory. What is full compatibility? In very few words, it's just the possibility of measuring any possible measurement at once with a single shot, in a single shot. So without disturbance of one observable on another. So in summary, this is a property that we expect to have in classical theory, but not in other theories different from the classical one. But we will see that there are some little surprises there. So the starting point, as I mentioned, is Heisenberg's gamma ray experiment, which actually was meant to provide some physical insight in the uncertainty principle, but turned out to point at a second problem besides uncertainty. So on one hand, in the paper, we have uncertainty due to the incompatibility of position and momentum. So one of the upshots of the uncertainty principle is that in quantum theory, there is no such state that you can measure, you can predict the outcomes of measurement of position and momentum with arbitrarily good accuracy. So you have a lower bound on the statistical predictions in any given quantum state, which is given by the Heisenberg limit. And on the other hand, it introduces the problem of measuring the system without disturbing it, because in the thought experiment, you have this gamma ray that hits an electron to detect its position, but in hitting the electron, it strongly perturbs the momentum of the electron.
Paolo, I'm sorry. Did you intend not to advance slides, or do you think that the slides are being advanced? Because
no, actually,
we only see the opening slide.
I'm sorry about that. No, I actually. So you didn't even see the summary.
We didn't see anything but this slide. Of course, we heard you, but so the slides do not advance.
So why is that? I'm sorry about these technical problems.
Share your screen, yeah, of course.
I'm doing that. So can you see that?
Yeah, perfect.
Okay. So
try to change the slide. Try to change the slide to see if it works.
Now I change the slide. Does it work?
Yeah, but no, change this one.
Yeah, I did.
No,
we see always the same.
Heisenberg gamma ray experiment.
No, okay, that's not working.
That's very odd.
I don't know what's going on.
Slideshow probably you should put, or PDF.
Okay, I see that there's something saying that my screen sharing is paused, but if I try to resume share, it doesn't work. So I need to stop and start from scratch.
Paolo, if I may advise, just switch to get out of the full screen mode and show it, just the way, this way, right?
This way, okay.
Yeah, and then maybe try advancing here, so it would be working, right?
Okay.
This way we can see everything well.
I have some animations. I hope. Okay, in the slides that are delicate, I will try to figure a way out. Anyway, so I was anyway moving to the next slide. So disturbance, as I mentioned, so in Heisenberg's paper, we have these two problems arising. One is the incompatibility of different quantities, the measurement, different tests that you can run on your system, and the other one is the fact that any measurement introduces a disturbance on the system. And the first part that we discuss, the talk will be about both issues, but the first part that we'll discuss is exactly the disturbance that is intrinsic in any quantum measurement, and also in theories beyond quantum, if some special features are provided. So let me just review something about disturbance in the modern language of quantum information theory, where the definition of disturbance is by negation. So you start defining what is a test that does not disturb the system. So it's a quantum instrument, a collection of quantum operations, such that if you coarse grain all the outcomes, what you get is a channel which does nothing on, to your system. So it's the identity channel. Of course, in quantum theory, this is possible if and only if every single quantum operation in the test is proportional to the identity test, which means that the information you gather with this kind of measurement is the outcome of this probability distribution PI, which is completely uncorrelated to your system. It's like rolling a die and doing nothing to your system. You get information which is completely uncorrelated from the system. So essentially, you don't gather information about the system. So no disturbance implies no information about your system. And this is a typical quantum feature. Any measurement that provides any arbitrarily small amount of information in your system will introduce some disturbance, will do something to the system which is not leaving it untouched. So we saw the definition of disturbance as leaving the state of the system untouched. However, in quantum theory, we have this other notion of information contained in a system, which is not only the state itself in which a system is prepared, but it's entanglement. So the idea that quantum information is actually entanglement is, for example, epitomized in this quote by Schumacher and Westmoreland in their famous book. So the idea is that in the end of the day, a transformation that does nothing to the system, does not disturb the system, must not even disturb entanglement, and vice versa. So what is nice in quantum theory is actually that there exist faithful states, so a special kind of entangled state, such that if you want to check whether your transformation does nothing on any preparation, you just have to check that it does nothing to this special faithful state. So you can turn this notion into something which is testable with an easy experiment. So this equivalence between disturbance on the local system and disturbance of correlations is an important one. And we will see that in general theories, it's not valid, might be not valid. So we have to make our definition a bit stronger. So what are operational probabilistic theories? This is a very short summary. I will try to say only the relevant things about a subject, which is wide, it's pretty big. So they will, on one hand, summarize some statistical aspects of the measurement process. So you will be able to describe measurements on systems which behave differently from quantum and classical ones. But you also want to describe within these theories processes, so transformations, tests, events. For example, something that in quantum theory we would call the collapse or the state reduction after a measurement. So the basic ingredients in the definition of an operational probabilistic theory are systems. So your theory must describe some types of systems, which are the types of systems that you will be able to run tests on. Then you have tests. Tests are collections of possible events with some set of possible outcomes, which are labeled by some index I. And in the theory, you will need to have a composition rule, which is a very simple one. So if a test has input system A and produces output system B, then you can connect it in a sequence with another test, which has the same input system as the output system of the first one. And then you get another test, which has input A and output C, like this one, which is the sequential composition of test T after test C. But also you want to be able to compose systems in parallel, make a composite system like this pair AB. And when you have a composite system like this, you want to be able to run tests independently on the two subsystems, C and D. So with a parallel composition of two tests run on the parallel composition of two systems. Then both composition rules have some neutral element, which is the identity test that you can apply after test A, so the identity for system B after A, the test A leaves it unchanged, or you can apply the identity for system A before the test AI, and also this composition leaves the test unchanged. As to parallel composition, you have a trivial system, which is a system, for example, in quantum theory would be the system of dimension 1 with a Hilbert space, which is just a complexes, multiplying vectors by a constant. So this kind of systems, this kind of composition of system A with a trivial system will leave the system A unchanged. And having a trivial system introduces tests with a trivial input or a trivial output, which have a special role in the framework, which are preparation tests, so the initialization of your experiment, and measurement tests, observation tests, which are collections of effects. So this is the same as a P of M in quantum theory, where you don't you disregard what happens to the systems afterward. Okay, let's move to the next slide. So on top of this merely descriptive language that I introduced, where you can describe compositions in a sequence in parallel and so on and so forth, you want to do predictions. And this ability is given to you by introducing the probabilistic structure that comes in this way. So you require that tests of the trivial system are just probability distributions. So for example, if you have a circuit like that with a preparation test and an observation test, clearly this is a test of a trivial system. So it must be a joint probability distributions for the outcomes of the preparation and the observation. And if you have a more complicated circuit like this one, well, also in this case, you will have a joint probability distribution for all the outcomes. So this object is actually a probability distribution for I, J, K, L, M. And then you want also to be able to describe coarse graining. So for every test with index set X, you can take a disjoint partition of this index set and construct another test, which is doing the same thing in the lab, but instead of asking what is the outcome of the measurement, just asking in which of the elements of the partition did the outcome fall. So this is a coarse-grained version of your test. So coarse-graining the outcome space. Okay, so as I told you, this scenario of theory is very wild. You can have their very weird theories, but it's often useful to introduce some special properties of the theory that allow you to prove something more and also have important physical consequences and interpretations. And one is causality. The first property that I would like to discuss is causality. We will use it especially in the second part of the talk, not in the first half. But causality essentially comes with two possible different definitions. One is stronger, and this is the first one that I introduced, and the second one is weaker in the sense that the first one implies the second one, whereas the other way around is not granted. So strong causality is the requirement that every time you do a test, like this blue test with outcome I, TI, you can collect your outcome I and use this information to decide what to do next. So you do a second test SJ with outcome J, which is labeled by I. So you read I and decide which SI to do as a second test. So this collection of possible events makes a legitimate test of your theory, which means that if you have strong causality, you can use information from tests to condition what you do next in an arbitrary way. You can do any conceivable conditioning. As a consequence of strong causality, you have the weaker version of causality, which is uniqueness of the deterministic effect. So there's only one way of discarding the system. In quantum theory, this would correspond to the fact that if you sum the elements of a POVM, you always get only the identity operator. Yeah, there's only one deterministic effect, which is tracing away the state. And this implies that if you take an experiment like this one, preparation and observation, and you sum over the outcomes of the observation phase, typically you would have a probability distribution for the outcomes of the preparation, which depends on the choice of measurement that you did. Not on the outcome because you marginalized, but depends on the choice of what measurement you did. So for example, in a Stern Gerlach, you can decide to measure on the vertical direction or resultant direction, and this would change the distribution of the states that you prepare. However, weak causality is the requirement that actually this dependency is dropped. So when you marginalize on the outcomes of the measurement, then the probability distribution of the states that you prepare is untouched. So in a sense, this means that you cannot signal, you cannot send information from the observation phase to the preparation phase, so backward in time in some sense. In some sense, because actually, causality is the property that breaks the symmetry between input and output. And you can see it both from the fact that I want to condition the second test and the fact that you have a unique deterministic effect, but not a unique deterministic state. So causality breaks the symmetry and selects a direction, input-output direction that can be identified with the arrow of time. Okay. Another property which is very important for operational probabilistic theories is local discriminability. So local discriminability is the property of theories where if you have two different stage, bipartite states, you can tell the difference with a local experiment. So there are Alice in her lab, Bob in his lab. They can do local measurements and then exchange classical information about the outcomes, and they're able to see that the two states are different. So this is not a general property. It's not granted in any theory. And in particular, this is a consequence, because if you have local discriminability and you have two different transformations, you can tell the difference just seeing the action on local states. You will always find a local state in the lab such that the output of the two transformations is different. So you can see that the transformations are different by a local experiment. But in the absence of local discriminability, you can have two transformations that look the same when applied to the local state, but actually are different. And you can tell the difference only if you have an ancillary system. So this means that, this, as you can understand, this affects the notion of disturbance, because local discriminability is the source of the coincidence that I mentioned before between disturbing quantum information as thought of as superposition in a local state, or disturbing quantum information in terms of disturbing entanglement. If you don't have local discriminability, it might be that you do not disturb the local state, but still you disturb entanglement. And this is a hint to the fact that the correct definition of disturbance must be given in terms of this dilated scheme in the general case. So let me say just a few words now about atomicity. So I mentioned coarse graining, and with reference to coarse graining, I will say that an event is atomic if it can be refined only trivially. So if we want to see it as the coarse graining of a collection of other events, then they necessarily have to be proportional to A itself, which means that this event is like an outcome of a test where if you want to introduce some extra information, it's just trivial information, the roll of a die, which give you this probability distribution, but there's nothing more, nothing more than that in this decomposition. So atomic events are indecomposable in a sense. Pure states are atomic states in causal theories. So pure states allow us to define another property, which is maybe the quintessential quantum property. It's the one that we used in our axiomatization of quantum theory, and is purification. So the existence of a purification is the following. So if I give you any state of your theory, mixed ones, you can always think of preparing it by preparing a pure state of a composite system and just discarding the environment, the ancillary system that you used. And then in quantum theory, you also have uniqueness of purification. So these are two distinct requirements: the existence of a purification for every possible state and the uniqueness of purification. So if you have two different pure states with the same marginal, purification of the same mixed state, then they are connected by a reversible transformation on the purifying system. So an example of a theory with purification is Fermionic theory. This is a theory which is rather different from the quantum one, even though it shares a lot of features with it. So the systems of the theory are collections of local fermionic modes. So you can identify the type of system by the integer n, which counts the modes that you're collecting in your system. And if you have a system of type n, then you have associated with it a Hilbert space which corresponds to n qubits. And you can choose a computational basis and form the basis for the tensor product. Pure states in this theory then correspond to unit rays, like in quantum theory, but with the caveat that the state space is divided into two sectors, the even sector and the odd sector, based on the number of zeros and one that appear in the case that you are composing, and superpositions of vectors with different parities are forbidden. So if you have just one local mode, you have, for example, state 0, state 1, you are forbidden it's forbidden to do superpositions, those two. But if you have two local modes, for example, you can superimpose 1, 0 and 0, 1, you can superimpose 0, 0 and 1, 1. And then you have superpositions, you have quantum superpositions, but it's forbidden to do a superposition like this one of 0, 0 and 1, 0, because these two have different parities. So if you describe states in terms of density matrices, they're block diagonal in this form. So an even sector and an odd sector, and the off-diagonal terms are always null. So this implies that you are violating local discriminability, because if you consider the state space of two modes, one is divided into even odd and the other one divided into even odd. If you take the tensor product, you have even, odd, odd, even, odd, and odd, even. However, the general rule that I gave you tells you that you're allowed also to see elements in these off-diagonal blocks and in this off-diagonal box, because still superposition of even plus odd and odd plus even is odd, and the superposition of even, and odd, odd is again even. And this means that the state space of the composite system is larger, it's double actually, than the dimension of the state space, the tensor product of the state space. And this is a signature of a violation of local discriminability. And indeed, in fermionic theory, you have to be very careful when you define disturbance of a test. So for example, you have, if you consider a mixed state, which is a mixture of an even and an odd state, this is represented by a block diagonal decomposition, as I showed before. You can run the parity test on this state. So measure the parity, and this measurement, it projects on the two blocks separately, which means that it leaves the global state unchanged. So it doesn't change the local state. However, you can purify your mixture with a purification like this one. So the marginal is actually a mixture of 0 and 1 with 1/2 and 1/2 weight. However, if you run the parity test locally on this purification, what you get is a mixed state. So you destroy the entanglement. So disturbance has to be defined in terms of correlation. What happens in correlation? So in the general framework of operational probabilistic theory, we define disturbance in this way. We say that the test is non-disturbing if its full coarse graining does nothing to bipartite state. So it acts as the identity also when applied locally on a bipartite state, on any arbitrary bipartite state. So now let's come to the definition of information that can be gathered from a test. So now we are in a setting where we do not require causality. So we don't have a symmetry between the input and output direction. We can think in principle of using a test like this red box AI to gather information about the output. So what happens at the output of the test, but also at the input, but also at the output of the test. So we can try to gather information on both sides. And how we can do that? So suppose that you control only the red box, and so the remaining part is described by deterministic preparation and deterministic observation. Then you would say that you are not, or you are collecting about information about the preparation if, in collaboration with the person who discards the systems, you can calculate the statistics of the outcomes and see a correlation between your outcome I and the preparation. So changing the preparation of your system, of your inputs psi, changes the distribution of the outcomes I, and the same about the output. So you can collaborate with the preparer and try to see the distribution of your outcomes. So you know the preparation, and then if the distribution is changed, that because there's a different test at the output. So you can gather information about what happens at the output. So this observation allows us to say when a test gives you no information about the input and no information about the output. And it's actually the case, for example, the test doesn't give you information about the input when the distribution of your outcomes I, PI, is factorized from everything else. So everything that depends on the preparation phase of the experiment is just discarded by a deterministic test, a deterministic effect. And so this probability is factorized from the probability of your outcomes, which means that your outcome is completely insensitive to the preparation. And similarly, you can give a similar definition for the observation. So what is interesting about this notion is that you can introduce the concept of a theory with no information without disturbance, which means if a test does not disturb, then it gives you no information about the input nor about the output. And then in a theory like that, where a test that does not disturb gives you no information, you can prove that the identity test must be atomic. So, which means that the identity is atomic if and only if you have no information without disturbance. So this property, which is one of the properties of quantum theory, can be generalized to operational probabilistic theories where the identity test is atomic. So you can reduce this rather complex property of the theory to this simple, easily checkable property of the identity test, which is indecomposability. So you cannot do a test that does not disturb the system unless you just roll a die and gather information which is completely irrelevant, independent from your system at hand. Okay, so this is the first nice result that I wanted to introduce, but we have some other interesting properties related to no information without disturbance, which are a necessary and sufficient condition, which is that you have no information without disturbance if and only if every reversible transformation theory is atomic. And then a sufficient condition, which is maybe a bit more surprising than the first one, which is if you have convexity and existence of purification, then you can rule out, you can say that this is sufficient to have no information without disturbance. You can rule out the possibility of gathering information without disturbing the system. So for example, Fermionic theory is a theory with purification and it has no information without disturbance. So one can wonder now what happens if the identity map is not atomic. So if you have information without disturbance. So if the identity test is not atomic, it means that it can be decomposed in a non-trivial way. And then this atomic transformation that feature in the decomposition of the identity can be proven to have this very important feature that if you multiply them, two of them, then you get a delta multiplied by the first one. So they behave like projections on orthogonal subspaces in quantum theory. So once you do the measurement and you see the outcome I, then you can repeat the measurement, you will see the same outcome I every time, and exclusively that one. And doing the test twice gives you the same effect as doing it once. So in a sense, this kind of information that you can extract without disturbing, which is the one given by this test made of atomic transformations this way, has some clearly classical feature. So it's a kind of measurement that is repeatable, it does not disturb, and you can, in principle, think of it as something which is really encoded in your system, like a classical property, not something like quantum outcomes or quantum values of observables, something like that. So this is intrinsically classical. So this decomposition induces a decomposition of your state space into a direct sum, in a sense. So you have states that pertain one sector, and every time you measure you measure this test that decomposes the identity on a state which belongs to a sector I, you will always see the outcome I. So you're measuring the ithness of your system, and this is some piece of classical information. This one you can measure without disturbing. It's the only kind of information you can gather without disturbing. So if the identity map is decomposable, it will be decomposable in this way, and this means that the state space decomposes in this direct sum of blocks which are mutually exclusive, and information must be spread among these blocks. You have a probability distribution of states in different blocks, and also measurements, so effects that essentially are, have the same form. Summarizing, this is all I wanted to say about information and disturbance. So we have no information without disturbance, which coincides with decomposability of the identity, atomicity of the identity. On the other hand, if the identity is decomposable, then you have information without disturbance. This kind of information you can gather is classical. And I would like to stress that we proved this in a very general scenario. We didn't even use causality up to this stage. So this is true in every conceivable operational probabilistic theory. So now coming to the second problem raised by the Heisenberg gamma ray microscope thought experiment, let's move to compatibility. So the fact that you have no information without disturbance is connected to the fact that in quantum theory you have incompatibility. So there are measurements that are incompatible with each other. But the question is, now we are in a wider framework. We want to go beyond quantum theory. So what does it really mean that two tests are incompatible? Well, let's take the first steps starting from quantum theory, and let's start from POVMs. In quantum theory, two POVMs are compatible if you can think of them as different marginalization of a joint measurement. So you have this POVM R with two outcomes, I and J. If you sum over the values J, you get POVM PI. If you sum over the values I, you get POVM QJ. So this definition captures the idea of collecting statistics for both measurements in a single experiment. So one can mimic this definition in the general case for tests of an operational probabilistic theory and consider two tests like this one, AI. So you have the events labeled by I, the second test BJ labeled by J. And you can say that these two are compatible if there exists a test like this one, C, which has two outcomes, I and J. And when you just discard the outcome J and system C, then what remains on system B is the test given by AI. And if you, on the other hand, marginalize on the outcome I and discard system B, then you have the test BJ. However, this is a bit too restrictive notion. We call it strong compatibility because we have a weaker notion of compatibility, which is implied by the strong compatibility, but it's not, the converse is not true. And the step beyond this stage that we want to do is that besides the statistical aspect of the measurement of the test, so the probability of getting outcome I or outcome J, which is the one captured by the POVM, the measurement, so discarding the system after the test. There's something else in the test, which is the evolution of the system when the test is run. So what we would call the state reduction in quantum theory. And this dynamical aspect of the test is an important part of the notion of compatibility. So in order to give a weaker definition of compatibility, we start by saying when it's possible to do a second test BJ after doing test AI. So we say that AI does not exclude test BJ. If you can run the test AI in a special way by running a test CK, coarse graining the outcome K in a suitable way, so you have this coarse graining of the possible outcomes K, collecting, gathering to the outcome I, and then you discard system B prime. In this case, you have your first test AI. But then if you change your mind, after having the outcome, you decide that you want to run the second test, B, on your system. Then there exists a post-processing test, P. So this is conditional. So you see that you have the outcome K, you decide which test to run depending on the outcome that you read, K. And then you have a second outcome, L. And then you coarse grain this pair of outcomes and discard system C. And what you get is the test B. So notice that here, what I'm supposing is that I ran the test A, and I had the outcome I. So this is very different from the quantum erasure, okay? Because in that case, you are able to erase the quantum measurement as long as you didn't get the outcome of the measurement. But if you get the outcome, it's irreversible process that is not erasable anymore. So here we say that the test A does not exclude test B if you can run A in a special way by suitably choosing this CK, such that after you get the outcome I, if you want to change your mind, you can do test B. So weak compatibility now is just the fact that the test A does not exclude B and vice versa, B does not exclude A. So if two tests do not exclude each other, we say that they are compatible. And one can easily prove that strong compatibility implies weak compatibility. Indeed, you can take as a post-processing here, you see, if this is true, you can just swap the two wires if you decide to do B instead of J, and then discard the second ancilla instead of the first one. So strong compatibility implies weak compatibility. but the other way around is not generally true. So now, what is a theory where you have full compatibility? So where every test is compatible with any other test. This would be the case of a classical-like theory, where there's no incompatibility, essentially. So one can immediately see that every test must be compatible with the identity test. So weakly compatible with the identity test. Actually, it should not exclude the identity test, which means that it will be compatible with any other test, because after you recover the identity test, then you can run the second test you want to do here after doing all your post-processing here. So full compatibility is connected to the notion of the relation between information and disturbance, because in a theory with full information without disturbance, what is full information without disturbance? It's the possibility of gathering every conceivable information, running any possible test of your theory without excluding the possibility of afterwards recovering the identity of the system. So setting things back and erase any noise that you did on the system, any disturbance that you did on the system, which means that not excluding the identity test is another way of saying that the test P does not disturb. So if you have, if every test does not does not exclude the identity test, the theory has full information without disturbance. And in this case, you're on the opposite side of the scale with respect to theories with no information without disturbance. So on one side, you have no information without disturbance, like in quantum theory. On the other extreme, you have theories where you can do, in principle, any test without disturbing. And these are classical-like theories. And interestingly, this notion of full information without disturbance is strictly connected with full compatibility of tests, because it's related to this possibility of any test of not excluding the identity test. And actually, the result that we have, and we are preparing the paper on this, is that this is a clearly necessary sufficient condition for full compatibility, having full information without disturbance. Whereas the necessary condition is that every system has a classical state space. So getting back to our decomposition of the state space into orthogonal sectors due to the decomposition of the identity, we have one extreme situation where we have no information without disturbance. There we have only one sector which spans the full dimension of the state space. Then we have the situation where you can gather some information without disturbance. So you have a state space that splits into orthogonal sectors, and each of those can have dimensions slightly larger than one, maybe much larger than one. And on the extreme, on the opposite extreme of the spectrum of theory with full information without disturbance, where you can prove that actually all these blocks corresponding to different outcomes of the test that decomposes the identity have dimension equal to 1. So this means that the state space of your system is like a simplex with states that are perfectly discriminable from each other, and you don't have any structure in these vertices. So they are one-dimensional spaces. So states living there are not decomposable further. And interestingly, this is a necessary condition, but not sufficient for full compatibility. Actually, we are working on a counterexample to this fact. I'll spend some words on this in the next slides. But first, let me say that I always said that this necessary condition is having a classical state space. So it's sufficient to have a classical state space, so the composition of the identity with subspaces of orthogonal states of dimension 1. This is not classical theory. This is just a classical state space. Why I'm saying so? Because it's possible to have classical state spaces with a theory where the composition of systems is not the usual tensor product rule. So you can have theories which are different from the classical theory only in the way in which systems compose to form a larger system, but the state space of each and every system is a simplex, like in classical theory. So if you have a classical state space, you can think of any measurement as a coarse graining of the measurement that decomposes the identity. So essentially, you have full compatibility of observation tests. So you're ruling out somehow uncertainty. So the source of uncertainty is that, for example, in quantum theory, measuring position and measuring momentum is impossible in a same experiment. Here you can run a mother experiment, which is distinguishing the pure states of your system, and the statistics of this experiment can give you the statistics of any other measurement that you do, because the other ones are just randomizations of this test. And a necessary and sufficient condition indeed for having classical state space is that all the observation tests are compatible. So full compatibility only of these special measurement tests where the output system is trivial. However, you can have situations where, so this is a summary of the conditions that we found, situations where you have full information without disturbance, which means that you have full compatibility of tests. This implies full compatibility of observation tests and no uncertainty. However, you can have situations where you have classical state space, so no uncertainty, full compatibility of observation tests, and still you have you don't have full compatibility of tests. You can even have a situation like this, where you have no information without disturbance. So the identity can be atomic, okay? So it means that from a statistical point of view, you can measure everything at once, but every time you try to measure something in a theory like that, you disturb anyway the system. And this is an interesting counterexample that we are preparing in collaboration, as I said, also with Marco Erba. So I would like to conclude just with this Venn diagram of situations that you can have. And here you have the full compatibility. So theories where every test is compatible with any other test. Here you have this yellow set is a set of no information without disturbance. And they touch here in the trivial theory. So a theory where you only have a system of dimension 1 and nothing else. A body theory where nothing happens, essentially. And then here you have the other properties with some examples scattered around. Okay, I think I said everything I wanted to say. So thank you for your patience.